Assalamualaikum and a very good day. Today I will be presenting about Discrete Maths Chapter 6, which is mission numbers. So let's get into it. So this is the table for content. This will be all the elements that we will be presenting throughout this presentation. So for the introduction is, what is mission numbers? So basically mission numbers are the way that numbers represented in the computer is also efficiently stored in arithmetic on them. So numbers are mainly divided into signed and also unsigned, where negative numbers in sign are represented using special techniques that we will be explaining throughout this presentation, which is 1 and 2 complement. So how do computers represent integers? So the computer only know zeros and also ones in order to build the sum of powers of 2. So to convert any given decimal number to binary is by dividing it by 2. Other than that, there are also base 8 and also base 16 depending on the convenience for the programmer of the computer. So, how computers differentiate between positive and also negative numbers? So, number one, signed and unsigned numbers. So, 0 means positive and 1 means negative. So, for one's complement, for the negative representation, it will invert all bits of the positive numbers. And for 2 complement, the negative representation is invert all bits of the positive number and then you add 1 to the number. Right. I will be explaining signed and also unsigned numbers. So first one, signed numbers. Signed numbers are integers that can be positive or negative, and they carry either positive or negative sign before assign the number. So for unsigned number, an unsigned integer is a whole number without a decimal that is always non-negative. It makes use of all bits to represent value from the range of 0 to 255. So for example, for this, 0 on the front means positive, and if you change the 0 to 1 means negative. Same goes for this, right? However, there are also disadvantage of signed and unsigned numbers. For signed numbers seems to have smaller range than unsigned numbers. And then signed numbers always have overflow issues, and both ones and two complements can suffer from overflow. So for unsigned numbers, there will be potential for confusion. In mixed operations involve both signed and unsigned integers, there can be confusion and also unexpected result. And another thing is no negative representation will be in unsigned numbers. So unsigned numbers cannot represent negative values, which limit their use in scenario. So how do we solve problems that I state just now in signed and unsigned numbers? So number one, we will be using ones complement.
Ones complement is a number representation technique which is used to represent a negative decimal number in digital form. Now, the following steps include change number to binary, which is change from a decimal number to a binary number. Secondly, the change from the negative binary number to the first complement, meaning that we change the ones to zeros, and vice versa, meaning that we change the zeros to ones. Thirdly, we add the numbers together. And number four is the n round carry, which I will explain later. Now, this is one of the examples for one's complement. Now, by using our matrix number, the last two numbers, which is 12 and 9, and by deciding that 12 is a positive number and 9 is a negative number, we should add those together. Now, the first step is actually to change 12 and 9 to binary digits. So 12 in base 10 is 1100, which is 1100 base 2. 9 in base 10 is 1001 base 2. Now, what are we going to do is change the negative decimal number, which is 9 base 10, which is equals to 1001 base 2 to 1's complement, meaning that we need to change the zeros and ones. So after changing, we should be able to get 0110 base of 2. Now, after changing the numbers to binary and changing it to 1's complement, we should add the numbers together. Therefore, this is the number in binary for 12. This is for negative 9. And what we're going to do is add those numbers together. So it's 1101 base 2 plus with 0110 base 2. Now, after adding, we should be able to get 10010 base 2. Now, if you can see, there is an overflow in the addition. However, with 1's complement, what you're going to do with the overflow is that you are going to take it out and then add it to the original summation. So what we're going to do is actually take this one here and then add it up with 0010 base 2. And after adding those two together, we should be able to get the answer 0011 base 2. And after changing it to binary, we should be able to get the answer 3 base 10, which is what 12 minus 9 actually is. Now, there are a few disadvantages when it comes to 1's complement. And those disadvantages include the fact that 1's complement faces problem when representing zeros. So as an example, 0000000 in 1's complement. Now, after adding these larger numbers, 1's complement have problems with the representation. As you could see here, the answer is wrong. Therefore, in order to combat this mistake or error, we could use 2's complement. Now, what is 2's complement? 2's complement is another binary number representation technique used widely in modern computers. Now, to obtain 2's complement in binary number, you actually need to invert all the bits similar to 1's complement, which I just showed just now, and add 1 to the least significant bit. 2's complement of a binary number is 1 added to the 1's complement of the binary number, and the overflow later, if there's an overflow, will be ignored. Now, these are the steps when it comes to 2's complement. It's the same as before, but with a bit of a change. Now, the first is to change the decimal number to binary, like before, and then change the negative binary number to 1's complement, which also means the same, meaning that you need to change the 1's to zeros and zeros to 1's. Now, the third step is a bit different. In terms of we need to change it to 2's complement, meaning that after we change it to binary, we need to add 1 to the change number, and after adding it together, we need to ignore the overflow if there's any. Now, this is the exact example with the exact same numbers, but this is by using 2's complement. Now, the steps are similar. Change all the numbers to binary. So 12 in base 10, you would get 1100 base 2. 9 base 10, you would get 1001 base 2. What we're going to do is change the 9 base 10 in binary, which is 1001 base 2, to first complement. So you should get 0110 base 2. Now, the third step is to change to 2's complement, meaning that after we've obtained the 0110 base 2, you need to automatically add 1 base 2 to that value. So after adding it, you should be able to get 0111 base 2. Now, this you need to plus with the value of 12 in binary, which is 1100 base 2. So after adding it all together, you would get 10011 base 2. Now, if you notice that there is an overflow when we've added all the numbers together. Now, in 2's complement, what you would do with the overflow is actually to just ignore the overflow and take the original 4 binary digits. So after getting that value of summation, you ignore the 1 here, and your final answer should be 0011 base 2, which is also the same as before. And after converting it to binary, you should get the correct answer of 3 to the base of 10. Now, all in all, understanding signed and unsigned numbers as well as first and second complement representation is very important for performing arithmetic and interpreting binary data in computer systems. Now, these concepts that form the foundation of how computers handle positive and negative numbers. Now, after we've understand that, that enables efficient and accurate computations for both hardware and software. That is all from me. Thank you very much.